Okay, so we're going to talk about completing the square a little bit. And then we're going to look at number 6, where we're going to basically prove a pretty famous formula that I'm sure you're all familiar with. And we're going to show, where does that come from? Is it just, you may have wondered that before. Where does quadratic formula, is that like some crazy calculus 5, I'm going to show you that it's actually very simple at its root. So not that the proof is that simple, but it's just completing the square. So anyway, let's get into it here. I'm going to show you a really simple example of completing the square. Okay, so let's say I had a number like 47. What is that number? Sean, what are you doing over there? That away, please. Sure. What's that number awfully close to if we're in the context of talking about completing a square? 49. It's awfully close to 49, isn't it? So what you can do here is say, okay, I can make this guy a little bit, make it a little bigger, make it 49. I did just change its value though, so actually 47 is 49 minus 2. It's kind of like a straggler there. And then I can talk about then, okay, so this number was really 7 squared minus 2. Okay, so that's a simple example of I completed the square. Now you might be going, okay, well, great. Okay, I guess you just showed that 47 is 7 squared minus 2, but what does that have to do with solving an equation? Let's look at 5a. So 5a has gave myself a little bit of room there. Who's got an idea? What's something I could add to this? He's awfully close to a perfect square right now. He's awfully close. What could I add to him to make him a perfect square? Anyone? Okay. So this is awfully close to x minus 1 squared. Because, well, what is the quantity x minus 1 squared? Well, that's x squared minus 2x plus 1. That's what that is. So what number could I add to this to turn it into a perfect square?
Plus 1.
1. Okay, so we'll use red for that, I guess. So what we show is that if you take this and you just add 1 to it, okay, now this, I've turned it into this perfect square. Are there any questions on what I just did? Okay. Now, so that might raise some red flags. You go, wait a second, can you just add 1 to the left side of the equation?
And you subtract 1 from the other side.
Yeah, as long as you do it to both sides, it's fine. So you can certainly add 1 to both sides of an equation. So that's really the step there. So in conclusion there, you're going, well, I can add any number I want to both sides of the equation. If I pick a number strategically, I can often turn this side into a perfect square. So this is my new equation. Like that. Okay, so what could I do next to solve the problem? Square roots, yeah, so square root. If this thing squared equals 8, then this thing has to equal positive or negative the square root of 8. Do you have any questions on that step there?
No.
Last step is just to add that 1 over. By the way, so add the 1 over. Well, I'll just keep it. I'll keep it as root 8 for now. So there was two answers to that original question. The original question, again, was what number, if you square it and subtract double that number, would you get 7? And it turns out there's two weird irrational numbers that have that property. 1 plus the square root of 8 and 1 minus the square root of 8. So anyway, the final answer, if you wrote it as two separate numbers, would be 1 plus, and then what's that is, if I simplify root 8, what do I get?
2 root 2.
Root 2. So you can see there's one positive number because 1 plus 2 root 2 is positive, and then 1 minus 2 root 2 is negative. So there's a positive number that has that property and a negative number that has that property. Both are, of course, irrational. So, how do we feel about that? Any questions? Okay, let's do one more example.
Sure.
Maybe, I don't know, C looks pretty good. Okay, so 5C. Is there some mystery number, or numbers, it could be two numbers, that if you square it and take away 3, that's equivalent to multiplying it by negative 10? Is there such a number out there? At least you can phrase the equation that way if you want. Okay, so am I ready to complete the square yet? Or should I maybe rearrange things before? Rearrange. So if I rearrange this a bit, namely add 10x to both sides and add 3 to both sides, you can write it like this. Oh. Give myself a little bit of room here. That make sense to everyone? Okay. So what number should I add to both sides here? Probably sleeping.
No.
6.
Okay, so the goal is to turn this into a perfect square. Okay, so what number is going there if this is x squared plus 10x?
5.
5, which means what number has to go there?
25.
25. Okay. So it turns out you need to add 25 to both sides to make it a complete square on the left side. So the left side, after adding 25, becomes x plus 5 quantity squared. The right side is 28. Okay. And now we can square root both sides. Oh, I forgot something. What did I forget?
Plus or minus.
Plus or minus. There's two possibilities. That x plus 5 could have been positive square root of 28, or it could have been the opposite of the square root of 28. And then I just subtract 5 from both sides. So it's negative 5 plus or minus. Now wait a second. Root 28. Do any perfect squares go into 28?
Yeah.
4 goes into it. 28 is 4 times 7. So it's be written as 2 root 7. Okay, are there any questions on any of those steps in that process? So before we go to the next thing here, what do you notice about the relationship between, it's in both problems we've done, the relationship between this number and this number? What is the relationship? It's half as big, right? Because we know that when you square a binomial, I'll do one more example for you. Say you had x plus, I don't know, 7. Well, 7 would be a pain in the butt. Well, sorry, x plus 7 squared. What you get would be x squared plus 14x plus 49. Okay? So there's a relationship between this coefficient and the number inside there. That number is half as big as that number. And then what's the relationship between this number and this number?
You square the number up there, make it bigger number.
Yeah, square it. So that's always true. If you're ever completing the square, half of this number gives you the number you're kind of looking for in there. Okay. And then this number squared tells you the number that you need to be adding to the term, sort of that sum to make it a perfect square. All right, so that being said, we're going to look at 6 is, just curious, who is I mean, you all know this formula, right? Okay. The question that we're asking here is, where does it come from? How do we know it's true? How do you know that? How do you know that if you have some formula, quadratic form formula, ax squared plus bx plus c equals 0, how do you know that the answer to that question, the x value that makes it work, is this weird expression? So that's what we're going to do. We're going to show where it comes from. Okay. And the key to that is that thing I was just talking about, that relationship between those three values. So suppose you've got some formula. By the way, guys, what's a circumstance? You're solving one of these questions. Why would you even want to use the quadratic formula? What kind of expression? That was kind of an open-ended question, but like,
It's fun.
no, maybe. I guess what I was looking for is if it's not factorable, right? So if you had like 3x squared plus 10x minus 19 or something, say that was your formula, you can't factor that. At least I don't think you can. Okay, how do I get a solution? Well, turns out there's a formula for it. So anyway, it's a little bit of background there. So we're gonna show that what if you just complete the square one time? Because in theory, you could always complete the square on anything, but say you complete the square on this general form, and then you derive a formula. Okay, that's what we do in mathematics a lot. You solve the general case, and you use that to solve other problems. So what do you think would be the first step here if I wanted to complete the square on this? That's a good idea. Yeah. Let's do two things at once. I definitely want to do that. That's for sure. But I'm gonna move this guy over, and I'm also gonna. Isn't it gonna be a lot easier if this guy is just a plain old x squared? So I'm gonna divide everything by a. So we're gonna do two steps at once. We're gonna subtract this c over, and also divide both sides of the equation by a. So if I divide him by a, I get just a plain old x squared. If I divide him by a, I get b over a times x. And then like Alyssa said, I'm gonna actually have that subtracted over as a negative z. So how do we feel about that? Does that make sense or no? Okay, so what's next? What would I like to turn this side into? Perfect, very good, perfect square. So we talked about the relationship between this value and this value. What's the relationship? It's half as big. Very good. So I need this to be a b over 2a. Half as big as that. And now to achieve that, what had to get added here? Remember that kind of triangle of relationships. What would I have to add to this side of the equation to make this work? That thing squared, right? So remember, when this was a 10, this was a 5, and this is a 25. So this is half as big, and then this is the square of this thing. So let's square it. And that tells us what we had to add. Does that make sense how I squared it? Now I can't just add that to the left side of the equation without also adding it to the right-hand side of the equation, so. We move this minus sign here to make it look a little bit nicer. Okay. I forgot something here.
Square.
It's a perfect square, right? Okay. So that equals, what can I do with this? Can I combine those into a single term? Is that possible?
Can you see?
You need them, they need to have the common denominator, right? So for just going back to real basics, if you wanted to do something like, oh, what's 7/3 minus 2/5, you'd have to find a way to have those have the same denominators. The way you do that in practice is you go multiply this by 5/5 and this by 3/3. And then, so there's actually a very easy way to make this thing have the same denominator as that thing. What would I have to multiply him by? 4a over 4a. Does that make sense? So now this fraction would be 4 times a times c over 4a squared. So now I can subtract them. So the top of my fraction is b squared minus 4ac. And then the bottom of my fraction is 4a squared. And then what do we do next when we complete the square? We square root. So we square root. So this is going to be plus or minus. Is the top a perfect square? Doesn't look like it, so I'll just write that as the square root of b squared minus 4ac. How about the bottom? Is the bottom a perfect square?
Yeah.
Yeah, I can square root that pretty easily. It's just going to be 2a. And then what? I just need to subtract this from both sides, right?
Yeah.
So look what you get. Now, these guys already have the same denominator, right? So it's already set up for us to combine them. Denominator was 2a. So you have negative b plus or minus the square root of b squared minus 4. So there you go. So that's the famous famous quadratic form. Okay, so that's
Well,
basically proves why does that formula hold? Why is it valid? So anyway, and I don't know, it's not trivial because if you turn that 2 into a 3, you can feel free if you're interested to look up the cubic formula. It is vastly more complicated. If it's even possible to solve it. And so, okay. Now. What?
We're talking about math.
Nine.
And what is the right arch to make it in?
What's the right what?
Angles to make the paper to the garbage.
That's a discussion for another time.
Yeah,
Let's talk
different
about-
Okay, so anyway, so 7 is just a little bit of, some review, hopefully, back from earlier algebra classes. How do you use that? How do you use that in practice to solve something? Well, I hope this convinces you that you're like, well, what this just proved is that anytime you might use the quadratic formula, you could just as easily just complete the square. However, completing the square might be a lot more complicated than just applying the quadratic formula. So we'll do 7A together. So 7A is just okay, so when you're trying to apply a formula, it's all about identifying which numbers correspond to which symbols. So which one's the A?
3.
3 is the A. 4 is the B. And then be extra careful that you understand that C is not 1, C is -1. So my answer then, we can go directly from this to the solution because of the formula, right? So -b, so what will I write? -b plus or minus the square root of b squared minus 4 times a times c. You can see why it was very vital to make sure that c was -1, because that would have changed the number there if we hadn't had that correctly identified. All over 2 times a. So let's simplify that. -4 minus. What do we get here?
28.
Because you're going minus -12. Okay. Is that the simplest way to write that number? No, because this is, this is 2 root 7. And now I can see all 3 of these numbers are divisible by 2. I can divide the top of the fraction by 2 and the bottom of the fraction by 2. You get -2 plus or minus root 7 over 3. Which is kind of an interesting number because it relates 3 primes. Okay. Let's do one more thing today. By the way, 9, I don't think I need to. I mean, if you guys are stuck, we can go over 9, I guess. But 9 is just asking you about, look at this formula and ask yourself, what condition would have to be happening in order for this to generate 2 solutions, 2 real solutions versus, is it possible that the answer is just no solution given this formula? Well, for it to be no real solution? Yeah, what if this thing under the square root was a negative number? So the last thing, number 8 is the last thing I want to talk about. Who's heard of the golden ratio? Maybe popular culture. If not, here, I'll just show you something real quick. Just show you what happens if you Google it. It's
It's been gone.
So I Google the golden ratio. There's all this stuff about it, all this sort of like, there'll be a lot of like mystical sort of, you said like a shell, right? Oh, yeah. I can briefly explain the shell thing to you. Who's heard of the Fibonacci sequence? Fibonacci. Here, I'll show you something interesting. This is a ratio that shows up a lot in nature, and so a lot of people will kind of be like, they'll find it kind of sort of mystical or just fascinating because of where it tends to show up and stuff like that. I'll show you a really simple example. So with the shell thing, this is a lot of times happened with the shell thing. Is you got, hey, look, I'm going to grow. I'm a little shell. I'm a nautilus. So start with 1, then I'm going to grow in a spiral. So this would now be 2 by 2. So I'm going to write 2 to represent the 2 by 2. And then the next square is 3 by 3. And the next square, what do you guys think the next one is?
4 by
5 by 5. And the next square is 8 by 8. And the next square is 13 by 13. And the next square,
21.
21 by 21. And I can maybe draw one more in here. I'll get the idea. The next one would be 34 by 34. And so if I was a shell, I might be growing out in this sort of spirally, you know. I had a professor once who was very triggered by the fact that people thought that the Fibonacci sequence occurred in nature because he just thought it was so profoundly obvious. It just made him very mad. Anyway, I don't know why. But anyway, so the Fibonacci sequence is, you don't need the spiral to show the sequence. The sequence is just, you go 1, 1. What's 1 plus 1? 2. What's 1 plus 2? 2 plus 3.
5,
8,
13,
21, 34, 57.
You get the idea. So I think why he got triggered was he just thought that if you look at the way, what he was annoyed by was that people would see this sequence and then see sort of things like that pop up, and he thought he was just like, well, obviously that's how it. I just always thought it was funny that he was so annoyed by it. Anyway, let's draw maybe 1 or 2 more terms here.
144.
144.
Brain say
233. Of course.
So the question is, now they call it the golden ratio. Well, what's a ratio? What if I divided this by this? I'd get 1 point roughly, so 233 divided by 144 is roughly 1.618. Approximately. Okay. And you might have noticed earlier when I Googled golden ratio, 1.618. Okay. But we're going to show you how to get the actual exact golden ratio. So, I guess the very minimum you got to write it down. Okay, so this gets back to, I think this is where like the ancient Greeks. So the weird part is you might start to wonder why the problem we're about to do is sort of like you start with a definition of what a golden ratio would be, and then it's what is kind of weird is why does it end up being the same as this Fibonacci sequence ratio? So that's something that you can, if you want, explore. But anyway, let's get into it here. So this says you have a stick. There is a way to cut it so that the ratio of the long piece to the short piece is the same as the ratio of the whole stick to the long piece. Oh, that's kind of a tongue twister, right?
Oh wait, the whole thing is one. Okay.
So here's the idea.
Stick is one.
Short.
Here's the stick.
No.
Okay. Can you cut the stick so that the ratio, this is kind of like Bob and his piece of paper a little bit. Let me show you an approach that is maybe just a total guess that might be kind of close, but not quite. Let's say we cut the stick in a ratio of like, I don't know, 8 to 5. So say I get a stick that's, 13 centimeters long, and I put a notch in it so that it's 8 and 5. Did I achieve the goal? The goal says the ratio, I'll write it out for you. It says the ratio needs to be long is to short as the whole stick is to the long piece. Does that make sense? So what's the long to the short is 8 is to 5, and the whole thing is 13 to the long is 8. Now, if you cross multiply this, you get 64 equals, whoa.
Very close.
That tells us that we got really, really close because those numbers are almost the same. An 8 to 5 ratio gets you pretty dang close. Okay. So how do we get the exact number? Yeah, there's a hint here. I gave you a hint, which was, this is a general, I've given you this hint twice, which is, this is a really good technique when you're trying to figure out some sort of mathematical ratio that has a certain property. You arbitrarily let some element of your diagram be 1. That simplifies things greatly. It's way simpler than going like A and B. So anyway, let this be 1. It says let the short piece of the stick be 1 and call the long piece X. So like Sean said, the whole stick is X plus 1. So my formula, if I go long is to short, okay, X is to 1 as the whole thing is to the long piece. It's the same setup. What can I do with that? Kind of like cross multiply, right? So X times X equals 1 times X plus 1. Uh-oh. This is another way of phrasing the question. Is there a special number out there in the universe where squaring it is the same as adding 1 to it? Does such a number exist?
Yes.
Yes, there's actually 2 numbers. One of them is the number that we're like thinking about. The other one's negative. Anyway, let's solve this. What's the first step to solving something like this? Very good, yeah. Get everything on one side. Like that. Now, what could I do to solve that equation? Is there maybe a formula I could use?
Quadratic. I don't think.
No. Good idea, quadratic formula. So if I identify that, hey, I should use a quadratic formula here, then you just go, okay, what's my A? What's my B? Oh, I made a mistake. It's actually -1. What's my C?
-1.
Okay, so quadratic formula says -b plus or minus the square root of b squared minus 4ac. Be super, super duper careful with your negatives there. All divided by 2 times a. So what we get is 1 minus square root of, let's see, 1 minus -4 is 5. So, how many numbers does that describe?
2.
There are 2. That's 1 plus root 5 over 2, and 1 minus root 5 over 2. Why is that not really a viable solution to the problem that we were asking? It's a viable solution to this. Certainly valid. It's just not really a viable solution to the original question.
It's just, you can't go back on the stick.
Right. It's a
Can't
negative
have
number,
negative
right? Yeah.
six.
So you can't be that's a negative number. So
Yeah.
1 minus root 5 is negative. So, yeah, you can't cut a stick so that one side is 1 foot and the other side is negative number of feet. Doesn't make sense. So this, we kind of reject this as being like not pertinent to the question. And here is that golden ratio. Notice that's X. So that was the actual ratio between the cuts. Now, for $1 million zillion dollars, what would happen if I took a calculator and went 1 plus the square root of 5 and then divided that by 2? What kind of number do you think would come out? That 1.618 number. So,
Then I get all the millions.
so this is they usually use phi, the Greek letter, to describe it. Phi is exactly 1 plus root 5 over 2, and that is approximately equal to 1.618. And perhaps mysteriously, that number shows up in that Fibonacci sequence. It's if you want to get technical, it's the limit of the ratio between successive terms in the Fibonacci sequence.
Whoa.
Whoa, indeed.
Brain broke.
Brain broke.
Come back to
We need